I wrote it twice, so why do I think about it? Okay, so chapter 4. Exponential and logarithmic functions. Exponential and logarithmic functions. So let's start with 4.1, exponential functions. Why do you think the absolute value function is called the absolute value function? Because it has absolute value. Why is the square root function called the square root function? Because it has, right. Why do you think the exponential function is called exponential? Right, and that is the variable. Exactly. So here is how it looks, a raised to x. This is the variable. As you see, f of x, right? That's the variable. Is the exponent, also called power. This is the base. The base is a number, of course. Now let me ask you a quick question. Can I raise -1 to the third power? Yes. Okay, I get -1. Can I raise 0 to the fourth power? I get 0. Can I raise 1 to the fourth power? 1. Yes. Can I raise, what else? 2 to the fourth power? 16. Can I raise 5 to -2? We can never forget this. This is a fraction, 1 over 5 squared, which is 1 over 25. So please remember, a to -n is 1 over a to the nth power. From everything you see here, this, and this are not allowed as the base for the exponential. In other words, I'm saying there is no negative number. This cannot be a negative number. Also, I'm saying this cannot be 0. And also, I'm saying that this cannot be 1. The only reason why these three are not allowed is because we will not be able to define this function. Okay? So what can the base be? So the base can be a number greater than 1 or a number between 0 and 1. Not 0, not negative, and not 1. So between 0 and 1, tiny, like 1/2, 1/4, 1/3. Or a number greater than 1, not 1. Anything greater than 1. Okay, that creates a little bit of a problem. Why? Because you will see the function has two different possible shapes. When it has the base greater than 1, it looks in one way. When it has a base less than 1, between 0 and 1, it looks differently. So we've never seen this before, right? For a function to have two different shapes. We did see polynomial functions. If the degree is even, it's a certain thing. If it's odd, it's a different thing. But here it's the same function. It depends on the base. So here's an example. Let's say 3 to the x power. This is an exponential function with a base greater than 1. And let's say another example here. Can anyone give us an example with a base less than 1, between 0 and 1? Good. I'm going to say 1/2, everything raised to x. So the first one has base greater than 1. It's the first category. The second one has base less than 1. Is the second category with 1/2. So expect two different shapes. So let's take a look. Let's start with the first one. F of x equals 3 to the x. First, we're going to look, yes, please.
I just want to make sure I understand correctly. It can't be 0, but it
The
can't-
base.
Right, but it can't be 1. So, but it can be lower than 1, but higher than 0.
It can be between 0 and 1,
But
any
it can't
number.
be 1, right?
It cannot be 1.
Okay.
1 it
Big issue.
cannot be. We will not be able to define the other one. And we cannot have a negative base, and we cannot have 0 or 1.
Thank you.
My pleasure. So, 3 to the x. We are asked to graph it. We have to graph it. We have to take a look at it and understand its properties. So, graph. Graph this function. Okay. When we're asked to graph a function, what do we start with? Always. We start with the always, forever. We start with the every time we graph a function, we start with the domain. Right?
Yeah.
Good. So now I'm going to ask, you are correct. The domain of this function is all real numbers. So x can be anything. X can be positive, negative, or 0. The base cannot be anything. But that is a number that is given to us most of the time. So indeed, I will call this function friendly. Like polynomial functions, this is a friendly function. Like absolute value function, friendly. I don't have to worry about the domain, all real numbers. Perfect. I'm going to pick -2, -1, 0, 1, and 2. And find the y coordinates, find the end behavior, and then graph the function. So let's plug in -2. 3 raised to -2. 3 raised to -2 is 1 over 3 squared. 1 over 9. Let's plug in -1. 1 over 3. So 3 raised to -1 is 1 over 3. Perfect. Plug in 0. Don't say anything, please. 1 second. A raised to 0 is 1, except when a is 0. 0 raised to 0 is not 1. So any number raised to power 0 is 1 unless that number, the base is 0, which is not the case here. The base is not 0. So when I plug in 0, 3 raised to 0 is perfect. Let's plug in 1. Very good. Let's plug in 2. Very good. So now I want to find the end behavior for this function. We have never studied the end behavior in this way. But this is special. This is a different function. Okay, let me go that way. 9, 3, 1. 1 over 3, 1 over 9, 1 over 27, 1 over 10,000, 1 over 10 million. Where am I getting to?
0.
Correct. I'm getting to 0. Okay. Now let's go the other way. 1, 3, 9, 81, 3 to the 5th power, 3 to the 10th power, 3 million. Infinity. We have never seen this before. What does this mean? When x approaches negative infinity or positive infinity and the function values approach a number.
No negative times 4.
This is called? We've seen this in rational functions. Horizontal asymptote. So y equals 0, horizontal asymptote at negative infinity only. There is no 0 on the other side. So that is a horizontal asymptote only at negative infinity. Good. Let's graph the function. From left to right, please dictate the first ordered pair. -2, 1/9. Of course, difficult. I'm going to say is this. Next ordered pair. Very good. Next ordered pair. Very good. And so on and so forth. This is 3 raised to x. the exponential function. Any exponential function with a base greater than 1 will look like this one. Not exactly the same points, but it will have the same shape. Okay. Let's look at the properties of this function. It has a lot of properties. Number 1, domain. You already gave me the domain. If you'd like to give it to me one more time. Very good. Remember, exponential friendly. 2, range. Awesome. Thank you. 3, X-intercepts. Of course. 4, Y-intercept. 0, 1. Very good. 5, increasing or decreasing on all its domain. Very good. Awesome. 6, 1-to-1
Yes.
by the
Vertical and horizontal.
horizontal line test is 1-to-1. 7, asymptotes. Y equals 0 at negative infinity only. Does it have an inverse function?
Yes.
Because it's 1-to-1. Of course. Has F inverse. We know nothing about F inverse, but I can graph it. And I know its domain and range. When I graph the function and the inverse on the same coordinate system, I always have to present this line. We know nothing about the inverse, but you can give me ordered pairs, precise ordered pairs, that will help me graph this function. So please give me a few ordered pairs.
1, 0.
Yes, 1, 0. Awesome.
3, 1. 1, 3, 1.
Very good. Here's the graph. The graph is not perfect. As you see, they should have been perfectly symmetric. They're not. With respect to y equals x. Because I think that y equals x should have been a little bit further to the right. Okay. So, can you say that you agree with my statement? Will you say that? The function, the exponential function with the base greater than 1 is always increasing, and so will be its inverse. Can you say that? Very good. Now, look at the inverse and say, this is a friendly function or not. Remember what I call friendly. I don't have to worry about its domain. What is the domain of the inverse? And remember, this has a horizontal asymptote. And this has a vertical asymptote. It's not a friendly function. So, what is the domain of the inverse? Correct. Why? Because it's the range of the function. What is the range of the function? So that's why the domain of the inverse must be 0 to infinity. And we know that, right? If the function is defined on A, range B, the inverse is defined on B, range A. Good. Perfect. Awesome. Let's look at the other shape now. What shape? The one with a base less than 1. So f of x equals 1/2 x. Yes, we haven't seen it yet.
Okay.
It will look totally differently than the previous one, although they are both exponential functions. So what I'm saying is there are two types of exponential functions. One with a base greater than 1 that is nice and increasing on all its domain, and the other one will look totally differently. And here's the joke, my joke for the day. Okay. Sometimes in the middle of the semester, I have students, I haven't had that in this semester, but sometimes they come to me and say, hey, professor, can I still get an A in the class? And I said, yes. as long as from now on till the end of the semester, your grade follows an exponential function with a base greater than 1. Okay. Good. So now we want to find the domain of this one. But it's an exponential function. The base is not important when it comes to the domain. Still, domain is all real numbers. I'm going to use the same little numbers, -2, -1, 0, 1, and 2. Please plug them in and tell me what you get. Let's plug in -2. Remember when we plug in -2 in x and we have a base that is a fraction, you know what happens? Good. So it's 4 indeed. Do I need to show how we get 4? Or we understand that we get 4? It's okay if you say show me.
Sure, I forgot. I remember all this.
Very good. That's okay. So if I have 1/2 raised to -2, I have 1 over 1/2 squared. By the rule, a to -n equals 1 over a to the nth power. That's how I wrote. A to -2 equals 1 over a to the second power. Now I have 1 over 2 times 1 over 2 is 1 over 4. When I divide by a fraction, I have to flip the fraction and I get 4. Better? Perfect. So now I plug in -1. It will be?
1.
But the base is 1/2. Okay, let's show that 2. Correct, correct. Do we all agree with 2 or do I need to show? Okay, so now let's plug in 0.
1.
Perfect. Let's plug in 1.
1/2.
Let's plug in 2.
1/4.
So now let's find the end behavior. Let's go this way first of all. 1, 2, 4, 8, 16, 32, 64, 128. Infinity indeed. This way. 1 over 2. I divide my cake into, I have a friend. Then I have 4 friends. And we're 4. And we divide it by 4. And then we divide it by 8. And then we divided the same cake by 16, and then by 32, and then by 64, and then by 128 people. How much will I get? The more people come to the cake, to share the cake with me, how much will I get eventually?
0.
Very good. Which means y equals 0, horizontal asymptote at infinity only. As I mentioned, and I promised, a totally different shape. Say it again, Sabrina.
Kind of like flip-flop.
Exactly. Perfect. Okay, so -2, 4. First point, -2, 4. -1, 2. 0, 1.
The graph is a little bit off the screen.
Oh, sorry. Sorry. This is the graph of 1/2 to the x. Totally different shape, only because the base is less than 1. Just a couple of different properties than the previous function. Pretty much the same, but totally different shape. So, let's go through the properties. Is the domain all real numbers? I'm going to go back to my list and I'm just going to check, and this will be for the base less than 1. Is the range still 0 to infinity? Range. The range on the y-axis. Still 0 to infinity. X-intercepts. Very good. Y-intercept. Yes, 0, 1. This is always the case for a pure exponential function. We're going to get to transformations in a minute, which will not going to be the same, right? But the pure exponential function has to cross the y-axis at 0, 1. Yes. Is this function increasing on all its domain or decreasing on all its domain? Yes, I'm going to put this in brackets here. It's decreasing for the one with the base less than 1. What about 1 to 1? Is this 1 to 1? Yes, it is. Check. What about asymptotes? Yes, but at positive infinity only. Does it have F inverse? Check, because it's 1 to 1. Let's graph the inverse. When I graph the function and the inverse on the same coordinate system, I must graph this line. Especially now, when the function is crossing that y equals x at this point. What will happen at that point? The inverse will cross at the same point. Why? Because all points on this line are 1, 1, 2, 2, 3, 3, 4, 4, 0.5, comma, 0.5. So when you reverse them, you get the same thing. So please give me a few ordered pairs so I can graph this function. So 4, negative 2. 2, negative 1. 1, comma 0. Good enough. This point, and I don't care for the rest. I have enough. This is F inverse. What do we notice? That if the function is decreasing because it has a base less than 1, what can you say about the inverse function? Also decreasing. However, this is not a friendly function. This function is defined everywhere. This one is not, only from 0 to infinity. This one has a horizontal asymptote, and this one has a vertical asymptote. Okay, so what we learned so far, let's summarize. We're talking about the exponential function, and we know that it has two different shapes. One which is increasing on all its domain when the base is greater than 1, and the other one that is decreasing on all its domain when the base is less than 1. Okay, let's look at a function with transformations now. An exponential, f of x equals negative 2 raised to x plus 1 plus 4. We're asked to graph using transformations. Graph using transformations. Like before, when we graph using transformations, we have to start with the base function and then build our function using order of operations. Can anyone say which function I used to create f of x? Which base function? It cannot be the absolute value, it cannot be the square root, it cannot be linear or quadratic. It must be, which one?
A to the x.
It's 2 to the x. The base function is the exponential function 2 to the x. Good. Then we have the first transformation on 2 to the x in order of operations. What will that be in order of operations? I'm changing x into,
X plus 1.
very good. What does that do to 2 to the x? When I change x into x plus 1, what will that do to 2 to the x? Which direction? Left one. Awesome. Left one. Number 2. Next one is the transformation on number 1. And in order of operations, I have negative 2 raised to x plus 1. Notice that we don't have parentheses here, right? So it's 2 raised to x plus 1 and then multiply the answer by negative 1. So what transformation is that? Remember, negative 1 does not touch x, but it touches y.
And flips the
Very good. Reflect with respect to WRT the x-axis. Perfect. And number 3 is a transformation on number 2, which is negative 2 raised to x plus 1 plus 4. What does that do to number 2? Up 4. Very good. Up 4. Okay? Everyone? So let's graph. First, we graph the base function. How do I graph 2 to the x? Is it increasing on all its domain, crossing at 0, 1, or is it decreasing on all its domain, crossing at 0, 1?
Increasing.
Increasing, because the base is greater than 1. Very good. So this is the graph of 2 to the x. Perfect. Then you told me to move it left 1. So this is my indicator point. Where will that indicator go? If I shift the entire graph 1 unit to your left, where will this point, which is at 0, 1, where will this point go? Very good. Negative 1, 1, right here. Awesome. Perfect. So this is the graph of 2 raised to x plus 1. Perfect. I hope you agree that these two functions still have y equals 0 as the horizontal asymptote. You agree? Perfect. What now? You said that in number 2, I have to flip. Where will my indicator go?
-1, -1.
Of course, very good, awesome. So here's my -1, -1. So this is -2 raised to x plus 1. Final step, you said that I have to take this graph where to now as the final step. Correct. Just remember one thing. These previous 3 functions had y equals 0 as the horizontal asymptote. If I shift this graph up 4, what do I have to shift first? The horizontal asymptote. From y equals 0, it will go to y equals 4. That's the first step. 1, 2, 3, 4. And now please tell me where my indicator is going. This. -1 still is on the same. -1, 3 indeed, right here. So here's the graph. And this is the final graph, which is f of x, -2 raised to x plus 1 plus 4. Now, can anyone give us the range of the final graph? It's no longer 0 to infinity, because this is not a pure exponential function. It has 3 transformations in it. -infinity to 4. Very good. That's the range of this function, -infinity to 4. Now any questions? Any questions? Now I would like to find the x and y intercepts algebraically. Find for the same function, x and y intercepts algebraically. Let's start with the y-intercept. I want to determine this point, see where it is. What do I have to do when I find the y-intercept for any function?
Set x equal to 0.
Thank you. F of 0. Let's do this together. 0 plus 1. 2 raised to 1. 2 times -1. -2 plus 4. Well, it happened. I really didn't mean it. I could have not known where exactly it crosses the y-axis. Okay, now let's determine the x-intercept. Obviously, it's just 1. So how do I find the x-intercepts for any function? I said, very good, f of x equals 0, which is -2 raised to x plus 1 plus 4 equals 0. Now I'm asking myself, like I always do, what type of equation is it? Is it absolute value? Is it linear? Is it quadratic? Is it quadratic in form? Is it rational? Of course it's exponential because that's what we're talking about. It is an exponential equation. Good. The variable is at the exponent. There is no other variable anywhere but the exponent. Perfect. So we have never seen this before. So let's use common sense. I don't know how to solve this, but common sense tells me to do what first? Move 4 over. Let's see what happens. Awesome. Again, I have no idea how to proceed, but it's clear that I'm going to do what next? Multiply, exactly, or divide by -1. So I have 2 raised to x plus 1 equals 4. Okay, now the left-hand side has a base. What is the base? 2, awesome. Now I'm hoping that I can present the right-hand side with the same base. Can I? So if the left-hand side is 2 to x plus 1, is there a way of writing 4 as 2 raised to a power? 2. So at this point, please never cross out anything. We're not simplifying. We're not dividing. We're just thinking. If 2 numbers are equal and they have the same base, what has to happen to these exponents? They have to be equal. Because if this is 15, 2 to 15th will never equal 2 squared. If this is -1, 2 to -1 will never equal 2 squared. So if 2 numbers are equal and they have the same base, it is a must that x plus 1 equals 2. There is no other way. If 2 numbers are equal and they have the same base, their exponents must be the same. So from here I have x equals 1. So this is our first exponential equation that we've seen in this class. So the ordered pair will be 1, 0, which is the x-intercept. Well, it's not exactly, but I'm going to say, okay. So this is 1, 0. Any questions? I would like us to look at a couple of applications here so we can see what does this function do? What is it used for? Where does it come into play? So let's take a look on page 475. Let's talk about, first of all, compound interest. That's one application. So when we deposit money in the bank or we borrow money from a bank, they compound the interest. And there are 2 ways. One is for the interest to be compounded continuously, which means every second, continuously. And there is a formula for it. You do not have to memorize these formulas. I'll explain. So this is A, this is P, E, I'll explain what E is, and then R, and then T. Lowercase r, lowercase t. The second possibility of compounding the interest is n times per year. N, lowercase n, times per year. It's a different formula. A equals P in parentheses 1 plus R over N raised to NT. P in parentheses 1 plus R over N, everything raised to lowercase n times T. These formulas will be given to you. But what we need to remember is what each and every piece represents, each and every letter. Okay, so A is the accumulated value. For example, let's say we deposit $1,000 today at a bank, and we want our money back. We want to withdraw everything we have 5 years from now. What we get back includes interest, and that's the accumulated value. The other way around, we borrow money from a bank. How much do we pay back? Well, we pay back with interest. So 5 years from now, we're not going to pay back 1,000, but maybe 1,200 or more, depending on the interest rate. And that's the accumulated value. What do you think P represents? Exactly. The amount of money we deposit or the amount of money we borrow. Lowercase r is the annual interest rate. Lowercase t, time, exactly, in years. Lowercase n is the number of times interest is compounded per year. Number of times interest is compounded per year. And the little e, I'm going to explain what it is Euler. That's the name of the mathematician who discovered it or showed what it means, if you want. And they named this number, like for example, pi. Pi is not named by after anyone, but E is named after this mathematician by the name of Euler. So this is Euler's number. Let's start with Euler's number. So if you go to your calculator, this is such an important number that it has two keys, actually. Here's the first one, second and E. And when you press enter, you will see it's 2.7. It's an irrational number, 2.71828, and so on and so forth. So one more time, you go to second and the division symbol and press enter. And you get 2, 4, 6, 8, 9 digits. Okay. Since E is a number greater than 1, if we make it into an exponential function with base E, will it be increasing on all its domain or decreasing on all its domain? Right, because it's a number greater than 1. Good. So that's our next step before we look at a problem. Okay. So there are two special exponential functions. One with the base 10, and the other one, of course, with base E. They are so important and so special that they have their own key in the graphing calculator. Look at this right here, right now, right here. Second E. And you can put it and or raise it to any power you want, whatever. That's the second key for E. Second and e to the x. Okay, here's another one. Right here, 10 to the x. Second, 10 to the x. And you can put whatever you want. Okay? So they also have special names. This one is called common exponential function. It's common. The other one, it comes in nature so frequently, it's called natural exponential function. Okay, so now let's look at a problem in which we are asked to determine the accumulated value. So let's say problem 53 on page 475. Find the accumulated value of an investment of $10,000 for 5 years at an interest rate of 5.5. If the money is compounded semi-annually, if the interest is compounded quarterly, and monthly, and then continuously. So I copied the information, but I didn't say which one is what. So we have to identify them. So what do you think 10,000 represents? Careful. Right? We are depositing 10,000. Is that okay? Principal. So this must be P. What does 5 years represent from the list of variables here? Indeed, T, indeed. What do you think 5.5 represents? Yes. However, be very careful. This must be changed at all times into a decimal number. You don't have to cross it out like that. I just wanted to make a point. Okay, very good. What does semi-annually represent? From all these variables, which one? So it's not exactly, it's n. So what do we mean by semi-annually? N equals? Semi.
0.5.
How many half of years are in a year? 2. How many quarters are in a year? How many months are in a year? And this is continuous, so it has nothing to do with n, right? So this formula for this will be A equals P e to RT, and the formula for these three will be A equals P 1 plus R over n raised to nt. So now let's put the information in that we have, and let's see what happens next. So I'll start with these three. And I will write A equals 10,000. I'm replacing the principal by 10,000 in parentheses 1 plus. I'm replacing the annual interest rate by 0.055. I divide by n. I'm going to name it X. You'll see in a moment why. Because it changes from 2 to 4 to 12. And then the power will be, if this is X, this must be X as well. And how much is T? 5. So this is 5x. I will put this function in the graphing calculator. So let's do that together. Because I want all three numbers at the same time. Can I do it step by step? Of course. Let me see if yes, I'm still recording. Okay. So in y equals, clear everything else. And let's put in 10,000. Parentheses, 1 plus 0.055 divided by x. Here's the key for x, right here, next to alpha. Close the parenthesis. Don't forget to put a caret now for the power. In parentheses, you know me, x times 5, or 5x, better. Let me know when you have this in your graphing calculator. So 10,000 in parentheses 1 plus 0.055 divided by x, everything raised to power 5x. And then let's go to second and table. What do I plug in? Two. Then I plug in 4. Then I plug in. That's it. So go across to the right and go up because we need digits. So here it is at the bottom. It gives us 13116.51. Yes, you need my help?
Yeah.
Oh, yeah. In order to plug in your own numbers, you have to go to table set, and you may have to make the independent variable in ask mode. And now it allows you to plug in any number you want, and it will give you the result on the right. Are we okay? So we go to second and table set, and we go to the independent to be in the ask mode. And now second and table will give us a blank, and you can put in any number you want. Everyone else okay? So we go to second and table set and make sure that the independent variable is in the ask mode. And now when you go to second and table, it will allow you to put in the numbers you want. Is that clear? Everyone else okay? Yes? Okay, so now I'm going to put in A of 2, which is 13116.51. Then A of 4, I scroll down, 13140.67, 13140.67, and the last one, 13157, so it's A of 12, 13157.04. The reason I created that function is because I didn't want to go back and copy it for 3 times. Do you have to put in a function? No, but I think it's easier if you do. Now, this one is only by itself. I will only write A equals 10,000, E to 0.055 times 5. So let's see what we get. If we deposit $10,000 at 5.5% for 5 years, if the interest is continuously compounded. So get out of there with second and quit. We don't need a table anymore. So we want 10,000. And then E, again, here's E, second, and this key, ln. And in parentheses, let me know if you need help, in parentheses, 0.055 multiplied by 5, and close the parenthesis. So do you need help with this?
Yes.
Okay, let's put in 10,000.
I got completely off the screen.
Oh, the second and quit. So every time, so you have this quit, second and quit takes you from that, but you're free. Yes, okay, so 10,000. And then E, which is second in this key, e to the x, second and e to the x. And in parentheses, 0.055 times 5 and close the parenthesis. Are we okay? Nate? Okay, perfect. So press enter now. So when you press enter, you will get 13165.31. 13165.31 for continuously compounded interest. Any questions? Any questions? Okay, I would like to look at one more problem before we move on. Either they're both on the same page, 475. You tell me what you are interested in. Are you interested to study the population of India? I will just read the first few lines. India is currently one of the world's fastest growing countries. By 2040, the population of India will be larger than the population of China. By 2050, nearly 1/3 of the world's population will live in these 2 countries alone. So 1/3 of everyone on the planet will be living in China and India by 2050. So that's one problem. The second one is about 1986 explosion at the Chernobyl nuclear plant. So that was a disaster, a total disaster. So which one would you like to study? Chernobyl, okay. Good, so let's read it. In 1986, so this is problem 66, page 475. I'm no expert, so do not listen to me, but this is just an opinion. Not just that a lot of people died because of that explosion, but the consequences of how other people who didn't die were just horrific. Their children and their children's children. Okay, in 1986, the explosion at the Chernobyl nuclear power plant in the former Soviet Union sent about 1,000 kilograms of radioactive cesium-137 into atmosphere. This is the background. The function f of x equals 1,000.5 raised to x over 30 describes the amount f of x in kilograms, so this is in kilograms, of cesium-137, which is the radioactive substance, remaining in Chernobyl X years after 1986. X is the number of years after 1986. So, what does X represent? How much is X for 1986?
0.
Of course. That's what x equals 0 represents. 1986 represents x equals 0. Okay. If even 100 kilograms of cesium-135 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Find f of 80. And determine if Chernobyl will be safe for human habitation by what year is this?
2066.
Exactly. So if these people are not already gone and they want to go back home, we want to check, according to the given formula, we want to check if they can go back in 2066. Maybe they're not alive anymore, but their children and their grandchildren, if they should go back, if they can live there. Okay. So first of all, let's analyze this function. What function is it? Is it linear? Is it quadratic? Is it rational? Of course, because the variable is the exponent. It must be exponential. Does it have a base less than 1 or greater than 1? Less. So will it be increasing on all its domain or decreasing on all its domain? Awesome. Very good. So all we can do is just plug it in. We don't have a way of finding the answer without a graphing calculator. So 1,000 in parentheses, 0.5 in parentheses, caret, parentheses, 80 divided by 30. So when I click enter, if the answer is more than 100, what will you tell these people or their relatives? You cannot go back. Not yet. Okay. What if it's below 100? You could say, according to the model, you can guarantee that according to the model, it's okay. So I will click enter, and we get 157, which means even 80 years after the incident. So it's 157.49, and the measurement unit, don't forget all these measurement units, 157.49 kilograms of cesium-137 is still present in the atmosphere. It's not safe. They shouldn't go back. Okay, so this is an application of exponential functions. A lot of applications. Okay, so we are ready to move on to 4.2 log functions. Logarithmic functions. We didn't know the name, but we already graphed those a few minutes ago. We didn't know. I didn't tell you. I hid that from you, but we just graphed them. In the inverse of the exponential, we graphed one like this, and we graphed one like this. What is the base here? If it's increasing on all its domain, it must be perfect. If it's decreasing on all its domain, it must be. Okay, here's a notation for the log function. Please do not get scared. It looks a little weird. It's nothing to be worried about. So here's the notation for the log function. Log base 2 of x. Log base 2 of x. Or log base 5 of x, or log base 1/2 of x. The base must be the same with the base of the exponential, either a number greater than 1 or a tiny number between 0 and 1. Any questions so far? Let me see if I